thank you everybody for coming again. So this is the third lecture. Today we're going to talk about powder diffraction, which is probably more relevant to you. Most of you we have access to powder diffractometers. Some of you will be using them now, or will be using them in the future. What I hope to do in this lecture is tell you about some of the theory behind powder diffraction and how you can get the most out of your instruments here in the sorts of experiments that you could do. So, what is powder diffraction? Well, remember that in order to observe diffraction, you have to, for a single crystal, you have to actually rotate the crystal, like we saw yesterday, with respect to the beam. So in a single crystal, for example, if we have a crystal, we have to rotate that with respect to the beam so that it will form the correct angle theta with respect to the incoming beam. Now in a powder, you have not just one crystal, but hundreds and thousands of crystals, very, very small crystals. Each crystal will be a different orientation to the beam. But at any one time, because you've got so many crystallites, you'll have all of the allowed diffraction patterns, all of the allowed diffraction planes. Some of the crystals will be angled correctly to allow diffraction to occur. So, in this example here, in the first crystal, we've got the 002 set of planes, and that set of planes is not at the correct angle, and so we don't see diffraction from that plane. But the 00, that should be the other way round. Looking at the lines, they're more closely spaced, so this should be 001, this is 002. So this set of planes is correctly aligned, the same crystal, and diffraction will occur. So from this crystal we'll see the what should be 002, and in this other crystal here we can see that now the 001 planes are correctly aligned and we see diffraction. So imagine then multiply that by hundreds of thousands, millions even of crystallites, depending on the size of your sample, all of which are randomly orientated with respect to that beam. Add to that the fact that on a lot of diffractometers you will rotate your sample to maximize the distribution of these with respect to the beam. And so we can see what that amounts to is that at any one time there will at least be some crystals that are correctly aligned. And so we receive all at the same time reflections from every crystal. So in the laboratory method, we have a single wavelength usually, usually copper K alpha, so copper K alpha radiation, so that's 1.5418 angstroms, typically for powder diffraction. It doesn't have to be, you can use lots of other wavelengths depending on what you're trying to do. So for example, I have a diffractometer where I have a silver tube, so different wavelength because I want to look at different despacings in the diffraction patterns. So the resulting diffracted beams can be measured and the corresponding despacings calculated. So Bragg's law again, wavelength, lambda equals 2d HKL sine theta HKL. So what we're doing is we need to vary theta, but we're keeping lambda constant. So in the standard experiment, that's constant. So we're working at constant wavelength, which we can get from a normal X-ray tube. I won't talk about the X-ray tubes. You know, you can look that up in most textbooks. But in this experiment, you have this constant wavelength. In other experiments, for example, on synchrotrons, you sometimes keep your angle constant and you vary the wavelength. So there are different types of powder experiments. But the standard laboratory experiment, so a synchrotron experiment, costs millions and millions of pounds or dollars, let's say, to set up a synchrotron. You can buy your X-ray diffractometer at a, well, I won't say a reasonable price, but at a price that most universities can afford. So this is the type of experiment that you'll be familiar with. So on most modern diffractometers, that you have computer control rather than the device shower camera that we spoke about on Monday. And this allows for fast and efficient data collection and subsequent analysis. So this is actually my old diffractometer. This is one I built myself. It was based on a Philips machine. So essentially, you have a collimated X-ray beam, which hits the sample, which is in flat plate geometry. At any one time, the diffracted rays are coming off in all directions, corresponding to the Bragg angles. In order to see those, you have some kind of counter. So on the old machines, it would be a scintillation counter. On the new machines, you have position-sensitive detectors or more sophisticated detectors, like charge-coupled devices. And essentially, you move this through a 2 theta arc, and and in order to minimize the angle that you have to go through, you also move the sample using a theta arc. So your actual arm on the diffractometer only has to move through around 45 degrees. In the modern, on your instrument here, you have theta geometry, which is slightly different. So you have a flat plate like this. You have your beam coming in like this. Oops, not drawn it very well. So you have your beam coming in like this. You have your detector somewhere over here, and various slits to make this nice and narrow. And so what moves in this type of setup is both the detector and the tube. So this is the tube and this is the detector. In this setup, the sample stays flat. So this is theta geometry, or Bragg-Brentano geometry, is this kind of geometry, and most modern machines are built in this way. There's a big advantage to keeping your sample flat. Anyone who's worked on a diffractometer like this will tell you, if you've got a very loose sample and you start to tilt the sample like this, well, some of your powder starts to go like that, and it's not a very good thing if you want to measure intensities. So this type of diffractometer, or more modern type of theta geometry, has really been around for quite a long time. Okay, so the first diffractometers were being produced by Philips, let's say in the early 50s. So I actually saw one of the very first diffractometers recently on a trip to Portugal, where they had kept one in a museum there. And I said, oh goodness, that's the same kind of instrument that I started my PhD on. So that's, I recognized it. And of course, in those days, what you had, your output, I'll show you that in a minute. So today, you have an output, and this is, you can see how long ago I drew this diagram. You can see from the computer that you don't see ones like that anymore. Well, before that, it was even worse. You had this on a piece of chart paper. So you'd have a bit of chart paper and your X-ray diffraction pattern was recorded like this. So this was your 2 theta. And if you wanted to do anything like refelt analysis, that would be very difficult. You had to find a way to convert your data from the chart paper into some electronic format. So this kind of instrument has been around for a long time, but what has changed in recent years is firstly things like new types of tubes that are very high intensity tubes to give you very well collimated high intensity X-rays, and most especially the detectors. There's been a huge advances in detectors over the last few years, so that now, in the past I would be collecting data for, let's say, 2 or 3 hours to get a nice good diffraction pattern on a diffractometer, whereas now on some detectors you can collect in a few minutes, a few seconds sometimes for the fixed angle detectors. So big advances in recent years there. So this is our diffractometer, but this is very similar. This is the theta geometry I was talking about. So your detector arm, so your tube arm and your detector here, and the sample. You can actually rotate, but the sample is mounted here. And this one is, this is the other diffractometer. So this is a D5000, I think, and this is our Expert Pro. What do you get out? You get out a diffraction pattern that looks something like this. This is hydroxyapatite, which is, some of you may recognize as the main component of natural bone, right? The main inorganic phase. So what you see is what the sorts of things I was telling you about before. Okay, so this is counts on here, this is 2 theta on here. So you see strong peaks and well spaced out here in this side of the pattern at low 2 theta, that corresponds to high D spacings. And here, weaker peaks, because the scattering falls off, your atoms are vibrating a bit more, they look a bit bigger, you get a destructive interference. And this scattering falls off here as you increase the Bragg angle. They're more closer together, the peaks, on this side, as you'll notice, on this side compared to this side, because remember that you are looking at, each of these corresponds to the reflection from a set of planes. Okay, so up here you have things like 100, 200. Down here you've got lots of high index planes. So I don't know, let's say 732 or something like that will be down over here somewhere. And the D spacing for this will be very much smaller than the D spacing for this, okay, because those planes will be more close together. And so down here at this side, all of the peaks will start to overlap each other. Over here, they're much more easy to separate out. So when we're trying to identify a compound, we really focus on this area of the pattern because the peaks are more spread out. So, the thing that you have to remember is in powder diffraction as opposed to single crystal diffraction. So yesterday, I showed you some Lowry photographs, essentially, of the reciprocal lattice. So what that was a photograph, and I could distinguish, for example, I could distinguish the 100 from the -00 from -100. Does that mean tripping over the wire or something? Now, that's because in 3-dimensional reciprocal space, and if I've got a single crystal like this, I can actually go to that reflection and measure that 100 distinctly as opposed to -100. It's in a different position. here, remember what we're seeing in our diffraction pattern. Our diffraction pattern is one-dimensional here. So we've reduced our three-dimensional diffraction pattern to one dimension. And that means that this scale here, this 2 theta scale, or I can convert it into D, because it's just D sine, remember the Bragg's law. This means that anything with the same D spacing will occur in the same place on this pattern. And that means that certain types of reflections, like 1, 0, 0, will be in the same place as -1, 0, 0, for example. This leads to what we call multiplicities of reflections. So something you have to remember when you're trying to extract intensities. So, for example, in the cubic crystal, any cubic crystal, the D001 is going to be the same as D010, same as D100, the same as D00-1, etc. So for this reflection, we say that D00 actually has a multiplicity of 6. So multiplicity equals 6. They all contribute to the intensity of that peak. So if this is our 001 peak here, then to get the intensity of D001, I have to divide by 6. And that's only approximate, because if, for example, this was non-centrosymmetric, then the intensity of 0, 0 minus 1 would not be the same as 001. So approximately, the intensity is 1/6 of the actual intensity that you measure. You also have to be careful when you have 2 different reflections that are not simple permutations of H, K, and L, but may also have the same D spacing. So again, in cubic crystals, you can easily work out that. So remember, so for a cubic crystal, 1 over D squared is equal to H squared plus K squared plus L squared over A squared. So you can, that's a simple calculation reveals that D511 is going to be identical to D333, because H squared plus K squared plus L squared here is the same as 3 squared plus 3 squared plus 3 squared. So it comes out as an identical D spacing. So in those cases, I don't expect the intensities of these to be the same, so it's difficult to extract the exact intensity for that reflection, because, you know, how do I guess which one has the higher intensity? These are the kinds of things that you have to be careful about, especially if you're going to do some kind of structure solution. So, what can you do with powder diffraction? And to be honest, I haven't listed all the things. I've listed what I think are the most important things. But I want to give you an idea of what you can do. So, we'll look at each of these. So things like qualitative analysis, Unitcell refinement, structure refinement, structure determination. This is what we were talking about yesterday. Quantitative analysis, phase transition studies, super lattices, kinetic studies. Now with these fast detectors, that's a real possibility. Crystallite size determination, that's the Scherer equation that I was asked about on Monday. Strain analysis and texture analysis. So all of these are things that you can do with your diffrantometer, and I'll show you some examples of each of these. So I would say about 90% of the world's powder diffractometers are used, I'd say that most of the diffractometer time on powder machines, about 90% I would guess, is used for qualitative analysis. That's, everybody, we run a diffraction service, and I would say that is most of what we do. What do people want to know? They want to know, have I made the right compound? How much of this second compound is in this compound? Did my reaction go to completion? These are the sorts of questions that you can answer with a powder diffractometer. So it's the primary role, and it relies on this basic principle that every unique crystal structure has its own unique powder pattern. So it's like a fingerprint. So you should be able to identify anything from its powder diffraction pattern. So so how do we do that? Typically we're using a database like the powder diffraction file, which you have here, and that is probably the most complete database of powder diffraction data, but it's not very complete. There's lots of other ways that you can supplement it, and I'll explain to you how you might do that. You can search the database in a number of ways, and there are a number of commercial search engines. Okay, they're not so expensive, and so I would definitely recommend that you invest in a small search, because you have the database. You might as well have a search engine that will help you to do this. So a typical search would involve the loading of a powder pattern and automatic measurement of the diffraction peaks. These will then be compared to those in the database, and you get a ranking according to how good the match is. To narrow the search, you can just say, I know what I put into my compound. You can say, I definitely won't have any, I don't know, germanium in this compound, or I've only put lithium, aluminium, and silicon in this compound. So you search for those things. So looking at this, we've got, okay, so typically you'll get a periodic table coming up like this, and so what we're looking for here, something containing sodium, calcium, phosphorus and oxygen, because that's what I put in, and I've said only these elements, and then I say look for something that has everything in it. Okay, so I'm looking for something that has each of those, or I could search for something that has at least one of these elements. So looking for byproducts that you might get. So in this example, it comes up with these answers. So here's my powder pattern here, and you can see I have a very good match here for sodium calcium phosphate. This is Na4Ca PO3 times, and I can clearly say that that is the right compound. So this is a nice way to do things, and it's fast. It's relatively fast to get. Okay, and it comes out with a powder diffraction file, which is stored in the database, which you have access to already. And so you can use this information. It's got a reference. You can go and find the original paper, and it's got, most importantly, it's got the space group and the unit cell dimensions where they have been recorded. So for me, as a crystallographer, that is very important information. And in this case, because the structure was not determined, we used that to determine the structure from powders. So we went and did a structure refinement. In fact, later on we managed to grow a single crystal and do that by a single crystallography. So, this slide is already a little bit old because all of these databases have many more entries now. These are available databases that you can subscribe to. You may do it already nationally. We have a national subscription. You can do, so things like ICSD The inorganic crystal structure database, oh, it's much more than 50. It's closer to 100,000 compounds now. And the Cambridge structural database is more like 200, 300,000 now. So a lot of structures. In fact, most journals ask you to deposit your structure in one of these two databases before you publish. So when you submit your paper for refereeing, they say, have you deposited your structure? And they ask for a reference number. So these are more or less compulsory databases to have access to. The other ones, there's some other things, crystal class and Unitcell data. That's that's quite a useful one. There's a protein database and a metals data file. Less useful, depending on what type of research you're doing. But certainly the first two, I think, are the most comprehensive databases that you can find. Now, these databases hold complete crystal structure information. That means not just the cell parameters, but also the atomic coordinates, the thermal parameters, everything you need to know about the crystal structure is recorded. So, looking at something like ICSD, this has also changed a little bit. This was our national service that we were running. We had our own interface to using ICSD, but ICSD have their own, so you can access that. And you can specify what elements there are in there, and you get, at the end, you can generate a simulated powder diffraction pattern. That's the beauty of this. It allows you, if your PDF database, the PDF2 database is nice, but it's not complete. There are lots of structures that are not there. So if you're searching for a particular structure, then it's very easy, once you've got the structural data, to generate this. So you can do lots of things. So if you have this, if you just have the paper, you can type in your coordinates, or if you can download the ZIP file, you can use something like lazy pulverix or PowderCell to generate your diffraction pattern. And then in PowderCell you can even upload your collected pattern so you can compare it. That's free, that's available online, anyone can download it. So these are very useful tools for you to use when you're trying to do phase identification. PowderCell even does some basic fitting to the peaks if you wanted to do that. Lazy pulverix was actually the original program. It's actually two programs, lazy, for the people that were lazy to set up the file, and pulverix, which does all the number crunching. So that dates back to the 1970s, late 1960s, but it's still available, and it's actually quite useful. I still use it a lot. You won't get a nice picture at the end, but you get the numbers, which are more important. So, assuming you've been able to identify your phases and to index them. So, to index the HKLs. So, if you have a powder pattern, you compare that with the literature. So using your PDF pattern. So here we have a list of HKLs and the d-spacings and the intensities. So this is the d-spacings and the intensities. So we compare that with our observed pattern and say, oh yes, this is 001 and this is 110, 002, let's say, until we've indexed half a dozen reflections, maybe more. You can then refine your Unitcell dimensions. What is critical when you're doing, now Unitcell refinement is very, very common. If you're going to do Reed-Felt analysis, you probably have to do this before you start your analysis on many occasions. You may just want to have your unit cell dimensions without doing a full Rietveld analysis because you might not know the structure. When you're doing it, some things are vital. First of all, measure the peak accurately. If you're trying to do a refinement, the last thing you want to do is to have something that is inaccurately measured, because you'll get inaccurate results. Then index the peaks, refine the unit cell dimensions, and a 0-point correction. Okay, now what is the 0-point correction? Every time you put on a sample onto the diffractometer, you might have a slightly different height of your sample. You might have a thicker sample, thinner sample. Okay, you might find that in between changing the diffractometer from doing high temperature work to doing standard room temperature work, that your that you are a micron in difference in height. Okay, this is accounted for. So what effect does that have? The effect is to shift all the peaks in one direction or the other, so you don't know exactly where true zero is. And that can be it can be a fraction of a degree. Usually it's a fraction of a degree. And so what you need to do is refine this 0-point correction, which corrects for that. Okay? Because remember that because this is it's a non-linear scale with d-spacing. Okay, so your 0-point correction can refine uncorrelated with your peak positions. So the 0-point correction, there's a lot of programs available to do this. You can even write your own. It's very simple. So it's based on this type of equation. Okay, that is actually, you can formulate that as a straight line, and you can actually fit it to a straight line. But for, let's say, the most complicated system would be triclinic, where you have to take into account all the angles. So, measuring the peak. Well, simplest way is to go into a program like WinPlotR, which is freely available. Okay, it's part of the full prof suite of programs, which you can download from the ILL in Grenoble. You can do that, and there's an automatic peak search. Okay, how does an automatic peak search work? Very simply, it takes the first derivative of your pattern. Okay, and so if you have a pattern that looks like this, and you take the first derivative, you'll get something like that. And it looks for this. So, very simple, it does that, but unfortunately it doesn't do it very accurately all the time. You have to be very careful that you have discriminated between the signal and noise, so you have different levels for that. And sometimes it will completely miss a shoulder. So you may have to play around with that a lot more than you would do to simply plot your pattern and measure it by hand. And if you're going to measure it by hand, make sure you focus in on the peak. Remember that you are limited by the resolution of the screen of your computer. And so it tries to compromise for that. And so sometimes you may get a fairly inaccurate reading for the center of your peak, unless you've blown it up to the sort of maximum. So always do that. You don't need so many peaks. You can do, depending on how many parameters, let's say a dozen peaks for a normal, 12 peaks for a normal structure, but you can do it on 6, depending on how many parameters you want. This is a program, French program that I managed to get hold of, which does it all for me, which does the refinement. So here's my 2 theta observed, here's my 2 theta minus 0, my 2 theta calc, and here's the difference. Notice, look at the difference of this one, the 110. Okay, this has the lowest 2 theta, so the highest D spacing. The resolution on that part of the pattern is much lower than the resolution in a standard X-ray pattern. So you've got to remember that because your D spacings are, it's a nonlinear scale, so you've got a pattern which is very, let's say, cramped in D spacings at the low 2 theta end. So it's very difficult to get an accurate measurement of D spacing at the low 2 theta. But at higher 2 theta, we get quite good numbers here. So this has the highest difference up here because it's the most difficult to measure accurately. So this one will give you an R factor, which tells you how good the fit is, so that's quite a nice fit. And we get here the cell dimensions. This was a monoclinic crystal. So cell dimensions and a 0-point correction, which you can use. What are the applications? So one of the things that you can do is look at the, for example, solid solution formation, or in this example, this is the thermal variation of lattice parameter in a cubic fluorite system. So this is BI3Y06, and you can set up your refinement to do this automatically, and you can see you can get very accurate. In fact, the standard deviations on each of those points is less than the size of the points. So you can do this very, very accurately if you take a lot of reflections. So, structure refinement. So the Rietveld method, we're going to talk about on Friday. So I'm not going to spend a lot of time on it today, just to say it's there. And the basic processes I'll go through at the time, but I mean, essentially you need an initial model, refine the background, unit cell dimensions, 0-point correction, peak shape, before you even get to the atomic coordinates. And then you refine these. So these are the basic stages. We'll talk about them in more detail on Friday. So I won't spend a lot of time on those. Structure determination. So refinement is where you have a model and you're trying to make that model better. Determination is where you are determining the model ab initio from the start, with no preconceived ideas about what the structure should look like. So you can do this in powders, but my word of advice, if you have a single crystal, use a single crystal. It's in single crystal analysis, this is routine. As I mentioned yesterday, I can do this for a normal crystal structure in a few hours. For powders, this is about a month's work to do this properly. This is not easy. So, first stage would be unit cell determination and indexing, just like we've done up to now. Okay, I've just been describing. Space group identification, then through systematic absences, then intensity extraction. You have to extract the intensities of each of these peaks, divide them by the multiplicity, have a guess at how they might be divided, whether it's centrosymmetric or non-centrosymmetric. Determine then your initial model, and I'll explain that in a minute. Then Rietveld refinement, then difference Fourier, just like in single crystal, difference Fourier maps to locate the missing atoms. And then a final Rietveld refinement. Let's go through each of those stages. So the unit cell determination and indexing. Right, there are a number of ways of doing it. Now, what happens if you have no idea? You've just come along, you've made this brand new compound, it doesn't fit to anything in the literature. You have the powder pattern, what do you do? So, first of all, you need to measure carefully the first 20 peaks. Okay, most programs will need at least that many to do the indexing. Then there are a lot of programs that do this automatically. So this is an old one, Visa, ITO, Trior, Dickvol. These are all available free that you can try to get the pattern. But it's very, very important for this. It's ultra important that you have very, very carefully measured peaks and that they have been corrected already for the 0 point correction. So an internal standard or an external standard, something like that to get you to make sure that you're confident of your D-spacings. Typically, they'll offer a number of possible solutions and you will have to guess which one is the right one based on their figure of merit. So Trior is quite a popular one. This is a structure that we actually, this is for bismuth zirconium vanadate, so this is a straightforward structure. We can see here, it's offered a solution here that's not, that it looks to be tetragonal. So you can see 2 axes equal, the 3rd axis long. It's indexed all the peaks and it's got a figure of merit here that's above 10. That tells me that that is a possible solution. Okay, no lines are unindexed, that's a good sign. So this kind of program can give you the unit cell, and from the systematic absences you can then work out the space groups. Space group assignment, just like we did the other day, is using systematic absences. Okay, so you just do that like you do for single crystal. Intensity extraction, we usually carry it out using the Pauli method or the Labai method. GSAS, which is the program that we tend to use, uses the Labai method, and that's quite good actually in GSAS. It works very well. Both methods use a refelt-like approach. Okay, so what they do is they fit the whole pattern, but assume nothing about how, they don't have a crystallographic model. All you've put in is your space group and your unit cell image, and some peak shape parameters. That's all. So you have no crystallographic model in there, so no model of the structure, and all it says is, I must have a peak here because this is my unit cell and this is my symmetry. How intense is it? And that's what it tries to do. So they rely on high resolution data since peak overlap needs to be minimized. And what you get out is a set of quasi single crystal data. So what they do is they divide everything by the multiplicity. You get a set of numbers that are basically HKL and let's say FOBS. And using that, or FOBS squared, and using that you can try and solve the structure using single crystal methods. So determination of the initial model we saw yesterday. In fact, I've missed out analogy, because analogy you wouldn't go through determination before. So Patterson vector density method we saw for heavy atoms, direct methods for structures that don't contain a separate heavy atom, or probabilistic methods with the sorts of methods that I talked about in my research seminar, so things like reverse Monte Carlo simulation, but other types of methods as well. So we've already described these, I'm not going to describe them again, they're identical. You're actually using the same software to do this. You've just created a pseudo single crystal data, you take it along and you try using Shell XS. So, the rest of the stages that we've already mentioned, Rietveld refinement, I'll talk about tomorrow. So, let's move on to some of the other applications. So, quantitative analysis. Quantitative analysis is not the favoured tool for quantitative analysis, but it can be useful. So, for example, for mixtures of phases, X-ray powder diffraction can be used to quantify different phase fractions present. In some cases, it may be the only method possible. So, for example, if I was to try and look at a mixture of alpha quartz and beta quartz, this would be the only way. They're both SiO2. I can't use chemical analysis. They're just crystallographic polymorphs of the same compound. So the only way I can do this is really by powder diffraction. There are lots of well-established methods. The Rietveld method offers a quick and accurate way to determine the phase fractions through multi-phase refinement. But accuracy is a problem. So typically percentage weights are plus or minus 5%. It's the normal detection limit for X-ray. So you have to be a little bit careful, but you can use it. If you want to look at some of the more traditional ways, there are the book by Alexander Klug, something like X-ray powder diffraction. I think it's 1G. It's a great big textbook like this. Maybe you have a copy in the library. It's got some of the very traditional ways of doing quantitative analysis. So there are various methods, internal standards, etc. One of the problems with this is that you have, this is not a simple linear relationship between, so if this is a mixture of A and B, then your scattering might look something like this. It's not a simple mixture. It's not a simple linear relationship between the amount of scattering you get from a compound and its percentage weight. So you have to be rather careful. But the Rietveld method is not bad. So here's one I did. What was this? Oh, this is bismuth. This is a Bimavox phase, Bisavox, and what we're looking for here are the different polymorphs. So this is on annealing this, looking at the decomposition of this into the different polymorphs. And so this is a three-phase mixture. So we're looking for the alpha, beta, and gamma polymorphs, and you're able to separate this out quite nicely. And you can see you'll get phase fractions for each of those polymorphs. So there's phase 1, phase 2, phase 3, and here's your phase fraction. So that's the weight fraction here is 39%, 48%, and around 12%, with an error on each of those. And I didn't show you I have a very nice plot where we showed that over time, where you can see each of those phase fractions develop over time. Phase transitions. Now you have a variable temperature stage. Okay, so you can monitor both temperature dependence and also compositional dependence. So compositional dependence. So this is a compositional dependence of a phase transition. So here we can see it again. Looks like a Bimavox. Okay, so going from the orthorhombic phase to what looks like then the tetragonal phase after a certain composition. So all that is possible by composition. You can do so you can do the same sort of thing. I haven't shown you one looking at temperature variation, but you can see that very nicely sometimes using these types of plots. Now with your instrument, you should be able to do that without any problems. So super lattices. Okay, so again, this is probably a Bloomer-Vox as well. So this is, what is a superlattice, first of all? We mentioned superlattices the other day. If you imagine a crystal structure which is defined by a unit cell like this, and sometimes, you know, you've got some atoms here and they repeat each other, but sometimes you'll get, let's say, an odd one, like a substitutional solid solution, where you need to order over a larger unit cell. Okay, let's say we had two of these together like that. So now your unit cell is not defined by this, but by this. And so all of the rest of the pattern is the same, but you've got ordering associated with the two X atoms here. And what that gives rise to in the pattern, so if you look at a normal diffraction pattern, you'd have peaks associated with the main phase, but then you would get little peaks associated with this ordering. Now, powder diffraction is great for that because you can look for those little peaks. And here we have one. This one is one of the orthorhombic Bloomer-Voxes, and here is I think that's an orthorhombic one. Here is the superlattice peak associated with that ordering, and that ordering occurs on the anion, the oxide ion sublattice. So very nice for that. You can measure it and you can find out what the supercell is and not just the subcell. And then this is something that I do a lot of. This is joint X-ray and neutron powder refinements. So this is bismuth aluminate. This is an oxide ion conductor at high temperatures. And what you can do is you can collect neutron data, and you have your X-ray data, and you can refine them together. So you put them together in something like GSAS, and you have just a single model covering both refinements. So you have to fit the X-ray data and the neutron data together. And as I mentioned in my research seminar, but I'll mention again here, so what are the advantages of doing that? So in something like bismuth aluminate, you've got bismuth, atomic number 83, something like that, 83. You've got aluminium, which is 20 something, yeah, 20 something. And oxygen, which is small, which is what, 8 or something? 8. These are the number of electrons, okay, that you can see. We've got 4 bismuths in this. So if you sum up 83 times 4 plus 20 something times 2 plus 9 oxygens, you can see that the oxygen forms a very small part of the scattering in X-rays. So it means that when you're trying to do the determination in X-rays, or the refinement in X-rays, it's very insensitive to your oxygens. You can hardly see them. So, but if we use neutrons, now neutrons are not scattered by electrons, but they're scattered by the nucleus of the atom. So this tiny little thing here. So they don't suffer from this destructive interference as we increase the Bragg angle. But it's a sort of non-linear relationship with scattering with atomic number. So this is Z. You can see that's so neutron scattering. Over here, but it means that oxygen looks big. Not so much smaller than bismuth. I can't remember bismuth, but bismuth probably is around 0.7 barns, something like that, and oxygen is 0.6 barns. So, very similar, you can see them. And it means that the oxygen is more clearly defined, and if we're looking at oxide ion conductors, we're very interested in what the oxygens are doing. Similarly, things like lithium ion conductors, those of you who might be doing work on batteries. Lithium, very small, just, you know, atomic number 3, X-rays, it's virtually invisible. So if you want to look at the lithium, see what it's doing in the structure, you have to use neutrons. So you can do something like this. You can take the X-rays to give you good positions for your heavy atoms, and neutrons to give you good positions for your light atoms, and together you get a very nice structure. A very accurate description. So here's your, oh, don't know what's happened there. My X-rays got inverted. The picture seems to have come out. Have you noticed? That's something with PowerPoint, I don't know. So there's an X-ray picture, and the fit, this is the difference down here. Here's your neutron picture. Okay, so again, it's fitting quite accurately to these two data sets, and you get, if you have the software, you can get pretty pictures like this that you can put on posters and things like that. So, again, 6 o'clock, it's time for today, so thank you very much for listening and coming along.
Any questions? Okay, if not, then we will have the last lecture on Friday afternoon. So tomorrow will be.
So the last lecture will be on reflow analysis.
Which room? TVSD, so the other building. On Friday. Okay, see you on Friday.